The dominant story in green hydrogen has always blamed technology when projects fail. Electrolyzers are too expensive, efficiency is too low, scale hasn't arrived fast enough. But when you look closely at why green hydrogen projects stall, miss final investment decision, or quietly disappear, the pattern is clear. It is not electrolyzers that kill green hydrogen projects, it is power prices. This distinction matters because it changes where attention, capital, and credibility should be directed. Electrolyzers are visible. Power pricing is structural. One can be improved incrementally. The other defines the boundary conditions of the entire system. Most green hydrogen debates focus on the part of the system that is easiest to point at, not the part that actually determines success or failure. At the most basic level, green hydrogen is electricity converted into molecules. Roughly 50 to 55 kilowatt hours of electricity are required to produce 1 kilogram of hydrogen before compression or storage. This is not a design choice. It is physics. That means electricity price alone sets a non-negotiable floor under hydrogen cost. Everything else in the system stacks on top of that floor. If electricity costs $20 per megawatt hour, power contributes just over $1 per kilogram of hydrogen. At $30 per megawatt hour, that contribution approaches $1.50. At $50 per megawatt hour, electricity alone exceeds $2.50 per kilogram. At that point, the conversation about electrolyzer cost becomes irrelevant. The project has already failed on arithmetic. Yet many hydrogen discussions implicitly assume power prices that are either temporary, conditional, or geographically rare. Ultra-low renewable prices are quoted without explaining how often those prices are available, how long contracts last, or what happens when the system deviates from ideal conditions. In reality, hydrogen projects do not consume electricity in a vacuum. They operate inside grids, markets, and regulatory environments that introduce volatility, constraints, and competing demand. One of the most common mistakes in hydrogen modeling is treating electricity as a static input rather than a dynamic system variable. Power prices fluctuate hourly, seasonally, and structurally. They respond to weather, grid congestion, fuel markets, transmission limits, policy changes, and demand growth from other sectors. Data centers, electric vehicles, heat pumps, and industrial electrification all compete for the same low-cost electrons hydrogen projects depend on. This competition is not theoretical. In many regions, new hydrogen projects are entering grids that are already constrained. Renewable generation may be cheap on average, but cheap hours are often oversubscribed. When hydrogen plants draw power during high-price periods to maintain utilization, their economics deteriorate. When they curtail to avoid high prices, utilization drops and capital efficiency collapses. Either way, the project pays the price. This is where electrolyzers are often blamed unfairly. When costs rise, it is tempting to point to stack efficiency, degradation, or capital expense. But in most failed projects, electrolyzers are doing exactly what they were designed to do. They are converting electricity into hydrogen. The problem is that the electricity they are consuming is more expensive, less available, or more volatile than the financial model assumed. The relationship between power price and utilization is especially brutal. Electrolyzers are capital-intensive assets. Their cost per kilogram depends heavily on how many hours per year they operate. High utilization spreads capital cost over more output. Low utilization concentrates cost into fewer kilograms. But maintaining high utilization often requires purchasing power during expensive hours, while avoiding expensive power reduces utilization. This trade-off cannot be optimized away. It is structural. Many hydrogen feasibility studies assume average power prices that look attractive on paper. But averages hide extremes. It is the tails of the power price distribution that break projects. A few hundred hours of very high prices can erase margins. Seasonal mismatches between renewable output and hydrogen demand introduce additional stress. Power markets reward flexibility. Hydrogen plants require stability. Grid congestion adds another layer of complexity. In regions with strong renewable resources, transmission capacity often lags generation. This creates localized congestion, curtailment, and price spikes. Hydrogen projects located near cheap renewables may still face high effective power costs due to grid constraints. Off-grid projects avoid congestion but inherit storage, overbuild, or idle capacity costs instead. There is no free configuration. Policy does not eliminate this risk. In some cases, policy amplifies it. Subsidies tied to hydrogen production can encourage operation during high price periods to capture incentives, even when power costs spike. This can make short-term economics look acceptable while long-term viability deteriorates. When incentives decline, the underlying power price exposure is revealed. This is why power prices kill projects quietly. Electrolyzers do not fail catastrophically. They operate as designed while margins erode. Projects miss financial covenants. Off-takers hesitate. Financing terms tighten. Expansion plans are delayed. Eventually, the project stalls without a single dramatic failure point. The narrative blames market conditions. The root cause is power economics. It is also why electrolyzer cost reductions, while helpful, rarely save weak projects. A 20% reduction in electrolyzer capex may reduce total hydrogen cost by 10%. A doubling of effective power price can destroy the entire margin. The leverage is asymmetric. Electricity dominates. Technology tweaks cannot compensate for structural power exposure. The geography of successful hydrogen projects reflects this reality. Projects that approach viability are located where power is not just cheap, but predictably cheap. Long-term contracts, stable generation profiles, low congestion, and limited competition for electrons matter more than headline renewable prices. This is why certain regions repeatedly appear in credible hydrogen pipelines, while others struggle despite strong political support. Time adds further pressure. Power markets evolve. What looks cheap today may not remain cheap over a 20-year project life. Grid demand grows. New industries electrify, price volatility increases. Hydrogen projects that rely on static power assumptions are exposed to future conditions they cannot control. Bankability depends on resilience, not optimism. The result is a widening gap between announced hydrogen capacity and hydrogen capacity that actually reaches operation at scale. Many projects clear early development hurdles but stall before final investment decision, because financiers understand the power risk embedded in the system. They see what the headlines do not. Electricity is the variable that refuses to behave. This is also why hydrogen competes with other clean energy uses in ways that are rarely acknowledged. Every kilowatt hour used to produce hydrogen is a kilowatt hour not used for direct electrification, data centers, or grid balancing. As demand for clean power rises, the cheapest electrons become scarcer. Hydrogen, as an energy conversion step, often loses that competition unless it delivers exceptional system value. None of this means green hydrogen has no future. It means its future is conditional. Hydrogen works when power is abundant, stable, and structurally cheap over long periods. It works when demand is co-located and flexible. It works when the system is designed around power realities rather than political targets. Outside those conditions, hydrogen struggles regardless of electrolyzer technology. If developers want to build hydrogen projects that survive, power strategy must come first, not last. Not as an assumption, as a design constraint. Projects that treat electricity as the central risk variable build differently. They accept lower utilization. They scale modularly. They secure conservative power contracts. They design for stress rather than perfection. This is where serious project analysis begins. Not with stack efficiency curves, but with power duration curves. Not with nameplate capacity, but with price volatility exposure. Not with targets, but with system behavior under pressure. If you want to analyze hydrogen projects at this level, H2 Hub by ReneEnergy exists as an authority platform for system-level thinking. It focuses on how hydrogen interacts with grids, power markets, and long-term risk, rather than treating hydrogen as an isolated technology. The goal is not to sell hydrogen, it is to understand when hydrogen survives. For viewers who want to independently pressure test assumptions around power prices, utilization, and delivery economics, We've linked professional project finance and planning models in the description. These are optional execution tools for scenario analysis, not inputs to this specific discussion. The hard truth is that electrolyzers do not kill green hydrogen projects. Power prices do. Until that reality is treated as the central constraint, the gap between hydrogen ambition and hydrogen delivery will continue to grow.